Okay, so this is your video in your air and air pollution unit, and this is going to focus on climate change and ozone loss. So greenhouse gases are any of the gases listed below. They occur naturally and they occur anthropogenically, which means that they are human caused. The one thing that I want you to notice is all of the anthropogenic greenhouse gases are natural, with the exception of the CFCs and the ozone. And everything over here in the natural is also anthropogenic, except the except the water vapor. So the gases that are in both columns, you need to specify where the source of that gas is coming from. Is it happening naturally? Is it a natural occurrence? Or is it something that's happening human related or anthropogenic related? Okay, so anthropogenic causes that add those greenhouse gases into the atmosphere. In the case of carbon dioxide, deforestation adds it. Any of the burning coal, oil, etc., burning of fossil fuels adds it. And then industrialization, the more that we manufacture and produce, the more that adds greenhouse gases, a lot of which is because it's burning fossil fuels to do that industrialization. The CH4 is the removal, the mining of the fossil fuels, landfills, stuff decomposes, that adds that methane in there. Increased agriculture, cows and sheep, as they poop, you're getting that. And then the melting permafrost, you're releasing that stored CH4, that stored methane. The nitrogen oxide is the fertilizer base, pretty much. Okay, so how our climate system works. Just as a refresher from your last video, greatest amount of energy is absorbed from the sun at the equator, and the least amount is absorbed at the poles, and so you have to move north and south through the Coriolis effect. Remember, Coriolis effect is simply as the liquid is going to turn as it moves north or south, because the equator is spinning around faster than the north or the south pole. Okay, so again, as a refresher, warm air is going to rise at the equator, moves to the poles where it falls. It's a lot more complex than that. This is just the basic line. So a modern Hadley cell, looking at how the air is moving, is going to look something like this. And so you see the different climates, again, are based on the temperature and the rainfall. The rainfall is really going to be controlled by how the air is moving. So you're seeing all those different weather patterns in different parts of the globe. Okay, so the convection cells. Those convection cells are going to move air and water. So we see the movement of those cells in different areas. So you see the winds going this way, you see the winds going this way. That's going to change climate and change vegetation patterns in different parts of the world. And so this is all, remember, this is all happening in the troposphere, which is the layer of the atmosphere that's right next to the Earth. Okay, so why do we care? Why is this important to climate change? Because all of these cells, this air movement, controls migration of insects, controls precipitation, which in turn controls plant growth, and then the temperature changes, controls where animals are living. So all of that goes back to what the climate is like, what the weather, rainfall, precipitation is, temperature is, and then that is caused by, or we are changing that, right? The whole big thing about climate change is that we are changing that because we are changing the amount of gases in the air, greenhouse gases in the air, which then impacts how the air is moving. So that's why we're calling it climate change now more than global warming, because it's not necessarily warming all over the globe. Our average annual temperature is rising slowly, but the more important thing is that it's not just getting hotter everywhere. It's that over here it's hotter, and over here it's colder, and over here it's more windy, and over here it's more stormy. It's just messing with the patterns that have already been there. So the role of ice in the system goes back to the albedo effect. Remember, the albedo effect is the absorption and scattering, so it bounces back all that sunlight. And the polar ice is going to have a huge albedo effect, right? It reflects a really large amount of the sun's energy, keeps the poles cold. So by not allowing that ice to absorb by bouncing it back, it keeps the poles cold. And then it ends up turning into a vicious cycle, because as stuff gets warmer, that pack ice or sea ice melts and the energy isn't reflected, so the less ice, the less energy is reflected back toward the sun, which becomes, so then the area becomes warmer, which means more ice melts, and so it just turns into this vicious cycle, with that increase in temperature beginning with increased greenhouse gases. So once you have a lot of ice melt at the poles, this poses huge problems for overall life, because that means that sea level is going to rise. So a sea level rise, think about here in Houston, what happens if sea level rises 5 feet? Half of Galveston is going to be underwater. So coastal regions are going to flood, which is a huge threat to islands, right? Like Bermuda, a lot of the Caribbean islands that we like to go to on vacation would be underwater. All of the major cities on the coast, like Houston, Galveston, all of the human life, I mean, it's some ridiculous number, like 3/4 of people on Earth live relatively near a coast. Changes the ecosystems, changes the biodiversity of all the estuarine and the ocean ecosystems, so it just messes up, relatively small changes in sea level, increases in sea level, change a lot about what's happening. So this is a very famous chart from the Antarctic ice core. So they're taking ice core samples and looking at those to look at how carbon dioxide has changed over time. And so they're noticing that this is definitely a cyclic process. Carbon dioxide concentration has increased and decreased over the millions of years. But what you're seeing is that carbon dioxide concentration in the atmosphere, which goes back to how many greenhouse gases are in the atmosphere, because carbon dioxide is a greenhouse gas. So the carbon dioxide and the temperature go hand in hand. I mean, you can see that chart looks almost the same, and they're two different things. So very, very closely matches, very significant correlation between the two. And we see an overall, it's hard to see from this chart, but there is an overall rise in carbon dioxide concentration. Droughts. So with increasing temperatures, we're seeing increased evaporation, which means we're seeing a lot more droughts. So drought conditions have increased by about 15 to 30% in almost every continent. Droughts are a big deal because water is so important. I mean, that's the bottom line. We need water. We need to have access to water and know that we will have access to water tomorrow and next month and next year. So that's, water supply and prices and wars over water. And we'll talk about those in our water unit a little bit later. Food security, which is the food supply and the prices, inability to grow food in certain areas. The people movement is a big deal. So, they're following water, they don't have food, they don't have access to water to clean, increases disease. Jobs related to water, increased drought, increases wildfires, then your loss of diversity because the plants and the animals don't have water, so you have this whole network chain reaction thing going on. Thermohaline circulation is going back to the movement of the different densities. So this goes back to looking at the Coriolis effect and how that relates to how that moves water and therefore how that moves air. So remember, Coriolis effect is just fluid moving. And we'll look at some videos in class to make a whole lot more sense of the Coriolis effect, because it's a pain in the neck. But remember that thermohaline circulation drives a lot, that density driven, right, drives a lot of the food chain and the Coriolis effect and all of the oceanic currents. Okay, so moving on to ozone. Ozone in the atmosphere, remember from that first video, it's contained in the stratosphere. We want it in the stratosphere. Ozone up is good. Ozone down in the troposphere is bad. Okay, so the higher the ozone, the better. We want some ozone because that absorbs and reflects the UVB light. So we need that ozone in the stratosphere. It's measured in Dobson's units, and it takes care of it, reacts with the UVB light coming from the sun and protects us from the UVB light. Okay, so the hole in the ozone is there. It has been clearly documented. I'm going to show you guys some videos of it in class. It changes in size every year. It comes back every spring. It goes away with the seasons. But there is a huge ozone hole over the Antarctic in the southern hemisphere spring. So in our fall is when this ozone hole is there. And it's there from, it is definitely an anthropogenic effect. It's there from increased chemical reactions. Okay, so ozone depletion. The Montreal Protocol was set in place in 1989, and it's a treaty with a whole bunch of different nations that's designed to protect that stratospheric ozone by phasing out the chemicals that deplete it. So what happens is the greenhouse gases that we're talking about getting put into the atmosphere anthropogenically end up reacting with the ozone, which causes the ozone to be depleted, which then doesn't allow the ozone to soak up the UVB light, and so that ozone layer that we have that's good for us in the stratosphere ends up disappearing. So that's the bottom line for ozone and climate change. And so we'll look at that in a whole lot more detail in class. There's a video there if you want to see it. Like I said, we'll look at some clips in class and talk about a lot more and go into a lot more detail with this.